Hello students, welcome back once again to the Batch of Excellence. This is Sagar Darvi, your chemistry teacher, and today we'll be learning continuation of a chapter that is Biomolecules. Well everyone, you all are aware in this series of lectures in the Batch of Excellence, we'll learn the organic chemistry not with respect to just the boards, but we also make sure that we are including all the important concepts as far as the competitive examinations such as JEE and NEET is concerned. So guys, keeping those facts in mind, in our today's lecture number 2 of Biomolecules, let me show you what exactly are we going to learn. Well, so to give you a background of what we have seen in the class number 1, and today is the continuation of that class. So in the previous lecture, we started the introduction of biomolecules, in which we started carbohydrates. We saw how we exactly should define the carbohydrate, what was the old age concept of carbohydrates. We also learned in modern ways, how do we define carbohydrates? And once that was done, we learned the classification of carbohydrates. We studied 2 simple methods of preparation of glucose. And then we studied some important chemical properties of glucose. Right, everyone? Okay. So, since we have already studied methods of preparation of glucose, let me tell you all those reactions that we studied. All those reactions, in fact, chemical reactions of glucose, which we have studied in the previous class, all those reactions satisfactorily explains the open chain structure of glucose, right everyone? All the reaction, all the chemical properties of glucose that we studied, all were with respect to the open chain structure of glucose. However, you will find there are some reactions which are still not shown by the open chain structure of glucose. Like when you draw open chain structure of glucose, we know that there is first carbon atom which you call it as aldehydic functional group. So we expect that open chain structure of glucose to show all the possible reaction which are otherwise shown by any other aldehydic group. However, if you allow this open chain structure of a glucose to react with reagents such as sodium bisulfite, it does not give you addition product of sodium bisulfite. In fact, it also does not react with ammonia. Not only that, if we allow this open chain structure of a glucose to react with Schiff's reagent, or if you carry out 2,4-dinitrophenylhydrazine test with the open chain structure, you won't find any reaction taking place. Also, it is observed that glucose shows no response to the addition of Grignard reagent. So these all reagents that we mentioned are the ones which otherwise shows reaction with aldehyde, but not with open chain structure of a glucose. Hence, that indicates that glucose might not be existing in the open chain structure of glucose. So what exactly is this mystery? There are some reactions which are perfectly shown by open chain structure of glucose, but just now like we mentioned, some reagents does not show any reaction with open chain structure, and hence this gives an idea that glucose naturally exist in a cyclic structure, that is in a closed chain form. Hence everyone, in our today's class we will be discussing cyclic structure of glucose as well as fructose. When we put them in a particular form, we call it as Haworth projection. So we'll be learning what is Haworth projection of glucose and fructose. Then we'll be talking about some important disaccharides, and of course we'll try to put those disaccharides also in the form of Haworth projection. So what all are we going to see? We'll be talking about sucrose, we'll be discussing structure of maltose, lactose and cellulose. Let me tell you, in a process of learning this disaccharide, we'll also come across some more terms like what is called as inversion of sugar. When we will study cyclic structure of glucose, we'll also come across a term called as mutarotation. So guys, all these things we'll be studying simultaneously, and then after that we'll be talking about some important polysaccharides and their structures, like we'll be discussing starch, cellulose and glycogen, and at the end we'll be discussing reducing and non-reducing sugars. So this is what we have to learn today. Let me tell you, this is a very important class today because all these subtopics that you see on your screen are the ones which you can expect to be asked in the examination. So everyone, let's get started with the cyclic structure of glucose. Well, just now we discussed why it is important for us to learn the cyclic chain structure of glucose, because there are some reactions which are expected to be shown by the open chain structure of glucose have not been shown by glucose. and that gave us an idea that glucose exists in a cyclic structure. So let us first understand how to get that cyclic structure. To get the cyclic structure, first I'll write down the open chain structure of glucose. So let's say we have open chain structure of glucose, which I'm putting it this way. In the Fischer's projection, first carbon, second, third, fourth, fifth, and then down here we have got sixth carbon atom. Everyone try to recall how we used to remember the structure. We used to take 6 carbon in a straight chain, right? While writing the Fischer's projection, first carbon we make it aldehyde, bottom carbon we make it primary alcohol, and then moving from fifth carbon upwards, we remember the position of hydroxyl group according to the stereochemistry as right, right, left, right. So right, right, left, and right. Rest of the valencies we satisfy with hydrogen atom. Alright everyone, so that is the open chain structure of glucose. Well, ideally, if you see the naturally occurring D-glucose, this is a D-glucose because at the lowest chiral carbon, OH is present to the right. So according to the DL designation, when you represent any molecule in the Fischer's projection, especially carbohydrate, when OH is put to the right, OH at the lowest chiral carbon, when we put it to the right, we call it as capital D sugar. We have seen the whole D family in the previous class, right? So this is nothing but D-glucose. All right, this is D-glucose. Now everyone, this open chain structure, like I said, naturally occurring glucose contains just 0.02% of open chain glucose. So almost negligible, almost like does not exist. Whereas remaining 99.98% is a mixture of 2 other forms of this open chain structure. So other than this, there are 2 more structures of glucose exist, which are a cyclic structure. So this total 3 structure exist in dynamic equilibrium with each other. How to get those remaining 2 structure is, look, you will see here the carbonyl carbon indicates this carbon is doubly bonded connected to more electronegative atom, making this carbon partially deficient. Because this carbon is deficient, the lone pair of oxygen atom from carbon number 5 will now attack at this carbon 1, 2, 3, 4, 5. So see, electron rich oxygen is attacking at the deficient carbon. This bond will break. Since lone pair is forming a new bond with carbon number 1, this oxygen will carry positive charge, so this H will undergo deprotonation. And C single bond O minus will accept the proton and will become C single bond OH. So that's how the open chain structure now forming a cyclic structure, where you will see carbon number 5 is connected to oxygen. Oxygen will be in turn will be now connected to carbon number 1. So we are getting a cyclic structure. How to represent that cyclic structure? Let me show you that. So this molecule will be in equilibrium with, and also in equilibrium with, well, look here. So first I'll draw it here. Let's say this is that carbon number 1. So at carbon number 1 now we have got 1 valency satisfied by hydrogen. Second will be satisfied by C single bond OH after accepting proton. Third valency will be this entire chain. And fourth is the new bond which will be connected through oxygen. So as of now, we are representing OH group which I am putting to the right. So C single bond OH. This is the H which I am putting it here. That is carbon number 1, second, third, fourth, fifth. Now see the fifth carbon is connected to oxygen of carbon number 5. Right, and this is CH2OH. First let's draw and then try and understand every aspect of the structure. So this is 6th carbon, 5th carbon has oxygen connected to carbon number 1, 5th carbons. Let's number it. This is carbon number 5 and this is carbon number 1. So you will see fifth carbon's oxygen, this oxygen I'm putting it here. So fifth carbon's oxygen is now connected to carbon number 1. I'm making sure I'm not keeping this corners pointed, because if you put it pointed, that might sound like that is a CH2 group. That is how we represent in the bond line formula. So to avoid the confusion, I'm keeping it rounded. I'm not keeping them as a corners like that. Well, so our fifth carbon, we have got H. Then we have got another OH at carbon number 4, which is to the right. Then we have got OH to the left and then again to the right. And remaining valencies, we are satisfying it with H. Well, the moment we got this structure, which is a cyclic structure of open chain form of a glucose, you will find now this cyclic structure has developed a newly formed chiral carbon atom. Isn't it, everyone? Look, this carbon wasn't chiral at all. It was C double bond O. Unsaturated carbon is never chiral. But now once this O attacked at carbon number 1 and this became single bond OH, this became a newly formed chiral carbon atom. Check all the 4 valency. One is H, other is OH, third is this entire group, and fourth is this O and C. O and C meaning I can consider it as OR. Right, everyone? So this is a newly formed chiral carbon atom. So what stereochemistry has taught us? If in any compound there is a newly formed chiral carbon atom, then with respect to that chiral carbon atom, 2 enantiomeric form will exist. So in this molecule, if this is a newly formed chiral carbon atom, so with respect to this chiral carbon atom, there will be 2 enantiomeric form will be existing, which we either call it as capital R and capital S, or you may call it as D and L. But while representing them in the form of a Fischer's projection, if at this newly formed chiral carbon atom, if I'm putting OH to the right in one of the enantiomeric form, then in other enantiomeric form, this OH must be put to the left. Hence, other than this cyclic structure, this molecule also exists in dynamic equilibrium with another form of a cyclic structure, where only difference will be at the newly formed chiral carbon, the OH will put it to the right. So let me first draw and then we'll explain all. So here. Okay. So let's say this is that newly formed chiral carbon. See, OH I'm putting to the left. Here we put it to the right. Now I'm putting it to the left. Second, third, fourth, fifth, and this is the 6th carbon atom, CH2OH. Alright, now carbon number 1 is further connected through oxygen linkage with carbon number 5. Right, everyone? Remaining valencies, we are going to keep it as it is. So this was 6 carbon, 5th, right, right, left and right, and remaining valencies are just hydrogen atom. You see, this is carbon number 1 and this is carbon number 5. So carbon 1 and 5 are now connected through oxygen, and the same carbon number 1 is the newly formed chiral carbon atom. So because carbon number 1 by attack of lone pair of oxygen atom have been converted to cyclic structure, we got newly formed chiral carbon atom. Because it is chiral carbon, the configuration of this carbon will differ in these 2 structure. So once if I'm putting OH to the right, in the other Fischer projection I have put it to the left. But rest of the orientation or the stereochemistry of rest of the carbon is still remaining the same. So this is what we were talking about. Open chain structure, the naturally occurring D-glucose is found to be existing in 3 forms which are in dynamic equilibrium, out of which this open chain structure is just 0.02%, whereas 99.98% are the combination of these 2 structures. Now you try and understand why were we saying that open chain structure of glucose does not respond to 2,4-dinitrophenylhydrazine, does not respond to Schiff's reaction, shows no reaction with sodium bisulfite or ammonia or Grignard reaction. The reason being that this structure This structure exists just for 0.02% in the open chain, but otherwise the whole structure is a cyclic chain structure. Well, now what exactly are this structure? Well, guys, I want you all to recall one important reaction of carbonyl compounds. When carbonyl compounds are allowed to react with alcohol in presence of dry HCl, they first form hemiacetal, then eventually form acetyl. Let me show you the reaction. Let's say if we have got some aldehyde, RCH double bond O, we are allowing it to react in dry HCl. So the lone pair of oxygen attack at H plus, which you call it as protonation. Upon protonation, this becomes C double bond OH plus. The moment we write it as C double bond OH plus, this indicates now this pi bond would want to break over oxygen to neutralize positive charge, which means this carbon is now going to be deficient. Earlier it was partially deficient, now the deficiency will increase even more. So since our reaction is with alcohol, now the first molecule of alcohol, let's write it as R-OH. Since oxygen of alcohol being nucleophilic, it will now attack at the deficient carbon. This bond will break towards oxygen, followed by deprotonation. Meaning, from alcohol, the effective nucleophilic part will be R-O minus. So see what we have got. We had R here, C, H, C single bond OH. I am putting it up here. And this is OR dash. Right, everyone? Hold on, guys. Yes, so if you look at this structure now, this is indicating that we have got a chiral carbon atom. Isn't this chiral? Yes, this is a chiral carbon. A chiral carbon carrying one hydroxy group and one alkoxy group. Such carbon having one hydroxy and alkoxy group is what we referred earlier in the chapter of carbonyl compound as hemiacetal. Right, everyone? So that is hemiacetal formation. And another important property, I'm just highlighting this H once again. This is hemiacetal. Imagine if we allow this hemiacetal to react with any reagent which has alkaline condition. So let's say if I'm allowing this to react with some alkaline condition. Because this H connected to O is protic, this OH will accept this H plus, this bond will shift back and alkoxide ions will leave. See, what are we going to get? RC double bond O single bond H, meaning this is going to regenerate back the aldehyde functional loop from where we started the entire reaction, which means the hemiacetal form when brought in contact with any reagent which is alkaline. Those alkaline reagents can accept the protic H and convert this hemiacetal back into original aldehydes. So original aldehyde function loop can be regenerated if hemiacetals are brought in contact with any alkaline reagent. Remember that we are going to use it later when we talk about reducing and non-reducing sugars. As of now, this is what you call it as hemiacetal, a carbon carrying hydroxy and alkoxy. Now everyone, have a look at this newly formed chiral carbon. At this newly formed chiral carbon, one group is hydroxy and other, if you see, a bond connected to oxygen and connected to carbon. So oxygen and carbon is nothing but alkoxy. If you look at this alkoxy, O must be connected to what? Carbon present in the alkyl loop. Hence this OC is an alkoxy group. That indicates this newly formed chiral carbon is nothing but hemiacetylic carbon. So I'll just note it down. This carbon is hemiacetylic carbon. Right? So at hemiacetylic carbon, you can see configuration is differing. In this structure, OH is present to the left. In this structure, OH is present to the right. Now let me name them. Guys, the structure which you have over here is what we are calling it as D-glucose. D-glucose. The open chain structure of a glucose in its aqueous solution exists in dynamic equilibrium in the cyclic form, which has got newly formed hemiacetylic carbon. At this hemiacetylic carbon, when you put OH to the right in the Fischer's projection, we call it as alpha isomer. So I'll call it as alpha D glucose. And when a cyclic structure is such where at the newly formed hemiacetylic carbon, if OH is written to the left in the Fischer's projection, this isomer is called as beta D glucose. Now, what are these alpha and beta? Alpha and beta are the terms used to indicate the two isomeric structure which are the cyclic form of open chain glucose, which are in dynamic equilibrium with this open chain form of a glucose. Whereas experimentally, if you find, you will realize that this beta D glucose is found to be existing almost 64%. Whereas this alpha form exists precisely, if you talk, it is 35.98%, which you can simply call is almost 36%. And this is, like I said, negligible amount, 0.02%. So 0.02%. So precisely this has to be 35.98. Well, guys, this indicate the existence of open chain glucose is negligible. What exists in nature is the closed chain form of the glucose, which exists in two isomeric form, alpha and beta. Now, if you compare alpha and beta and try to find out what kind of isomeric relation they have, guys, tell me one thing. The configuration is differing only at carbon number 1, whereas at rest of the carbon, the configuration exactly is the same. Which means if I try to compare them as a mirror image of each other, would they be mirror image of each other? Absolutely not. So alpha and beta isomer are the non-mirror images of the same compound. So non-mirror images of the same compound is what we refer it as diastereomers. So I will say alpha and beta isomeric form of a cyclic structure of glucose are the pair of diastereomers which differ in their configuration only at newly formed hemiacetylic carbon. This hemiacetylic carbon is also known as anomeric carbon. So when two diastereomers or the pair of diastereomer of a glucose which differ in their configuration only at anomeric carbon, then such isomers are referred as anomers. So guys, new term after epimers for us is anomers. What are anomers? Anomers are pair of diastereomers which differ in their configuration only at anomeric carbon, meaning at newly formed hemiacetylic carbon, you call them as anomers. Now see, it will make sense to you guys how we defined epimers. When we defined epimers, remember, D-glucose and D-mannose are C2 epimers. D-glucose, D-galactose are C4 epimers. So epimers are again pair of diastereomer, but they differ in their configuration at any one of the chiral carbon other than anomeric carbon. So we used to call them as epimers. Now, anomers are the one which will only differ at anomeric carbon. So alpha D-glucose and beta D-glucose are referred as anomers of each other because they differ in their configuration at anomeric carbons. Alright, so hemiacetylic carbon can be referred as anomeric carbon, and because configuration is differing at anomeric carbon, we refer them as anomers. Alright guys, well, now let's try and understand something else as well. Well, suppose if you talk about this beta D-glucose and if you separate the crystalline form of beta D-glucose, you will find it has a melting point of 150 degrees Celsius. Whereas if you separate alpha D anomer, alpha anomers or alpha D glucose and its crystalline form, you will find it will melt at 146 degrees Celsius, meaning these two are independent form of glucose which exist in nature. But imagine if you take alpha D glucose and make its aqueous solution. If you take alpha D glucose and make its aqueous solution and find out its specific rotation, you will find that it has a specific rotation of plus 112. So alpha is optical rotation. This alpha is not related to the anomeric alpha. Okay, this is optical rotation. In the bracket, when we mention that indicates a specific rotation of alpha D glucose is measured to be plus 112 degree. So if you take a freshly prepared aqueous solution of alpha D glucose, it shows specific rotation of plus 112. But if you allow that solution to stay for a while, you will see the specific rotation changes from plus 112 and settle at plus 52.7 degree. That is the specific rotation which is observed after settling it for some time. Similarly, if you take beta D glucose crystalline form and makes its aqueous solution, a freshly prepared aqueous solution, and when you check its specific rotation, immediately you'll find it will show a specific rotation of plus 18.7 degree. But if you let the solution stay for a time, you will find sometime gradually this rotation will increase and settle at the value of plus 52.7 degree. So guys, what are we observing? When we are taking individual anomer in its crystalline form and making its aqueous solution, it is showing some optical rotation. But gradually that optical rotation is changing and settling to some equilibrium value. This change in this specific rotation of freshly prepared aqueous solution of the anomeric form settling into an equilibrium value of plus 52.7 is what we refer it as mutarotation. So guys, what we have explained over here is a phenomena of mutarotation. So if anyone asks you what is mutarotation, you will say a freshly prepared aqueous solution of alpha anomer of D glucose shows specific rotation of plus 112 degree. Similarly, a freshly prepared aqueous solution of beta anomer of glucose shows specific rotation of plus 118.7 degree. But when these solutions are allowed to stay for a while, their optical rotation gradually changes and settles at the equilibrium value of plus 52.7 degree. This gradual change in the specific rotation of aqueous solution of the crystalline form of pure anomer is what you call it as mutarotation. Alright guys, so few terms we learned here. Today we learned something called as anomer, something called as anomeric carbon or hemiacetylic carbon. We saw how open chain structure exists in equilibrium with closed chain structure which exists in the major proportion, and then we also learn a term called as mutarotation. Well guys, now if you look at this closed chain structure, this closed chain structure can be represented in its Haworth projection. Let's try and understand what is that Haworth projection is. To understand the Haworth projection, you need to first understand a reference structure which is pyrene. So suppose if I talk about pyrene, you write pyrene like this. Six-membered cyclic structure having one of the heteroatom oxygen. So if you compare this pyrene with the alpha or beta anomeric form of glucose, you will find similarity. Just like we have got oxygen, we have got oxygen here, and rest of the 5 are carbon. 1 2 3 4 5. Likewise here 1 2 3 4 5. Just that pyrene is unsaturated. This is not the unsaturated one, but structure is resembling to pyrene. Hence, keeping pyrene as a reference, we can put this beta D glucose or beta anomer of glucose similar to pyrene structure, and when the way you represent that structure is what you call it as Haworth projection. So how do we represent Haworth projection? Let us understand that first. Look, while putting the Haworth projection, what we do is we first make an arrangement. Everyone here? Hold on everyone, I'll just draw it properly. Okay, let's say this is carbon number 1, carbon number 2, carbon number 3, carbon number 4, carbon number 5, and this is carbon number 6. I'll just mention the number here. 1, 2, 3, 4, 5 and 6. Okay, everybody here? Now look, suppose if I'm drawing a beta form of a glucose, alright? So carbon number 1 is that hemiacetylic carbon. So hemiacetylic carbon meaning anomeric carbon is this, which has got one group connected to it, OH, and other valency is H. So see what I'm doing now. I'm putting that OH above the plane, H below the plane. Now for the remaining OH group which is present at second, third and fourth, always remember, the group which is present to the right in the Fischer's projection, we put it downward in Haworth projection. The group which is present to the right in the Fischer's projection, we put it below the plane or downward in the Haworth projection. I'll note it down. Group at RHS in Fischer's projection goes downward in Haworth. Okay, the group which is present to the right hand side in the Fischer's projection, it will go downward in the Haworth and vice versa, meaning the one which is present to the left will be represented above the plane. So at carbon number 2, OH is to the left, OH is to the right, so it will come downward. At carbon number 3, OH is to the left, so it will go up. At carbon number 4, OH is to the right, so it will come downward. At carbon number 5th, we have got this oxygen. This is the oxygen, and there is one H and CH2H. So by convention, let's say if I'm putting CH2H upward, which is this carbon number 6, which is this, remaining is H. So remaining valencies we can just satisfy by hydrogen atom. Now this is what you call it as Haworth projection of the glucose. Now let me tell you, this Haworth projection of a glucose will be identified as a beta because of, look at this arrangement carefully. You will observe carbon number 1 and carbon number 5 has flanked the oxygen atom. Carbon number 1 and carbon number 5 has flanked the oxygen atom. So you always have to look at the 2 carbon in which the oxygen atom is flanked. So the 2 carbon in between where oxygen atom is flanked is carbon number 1 and 5. At that carbon the valencies are, one is CH2OH and other is OH. So if you observe the 2 valencies of carbon number 1 and 5 both are above the plane or both are on the same side of plane, then that indicates it's a beta anomer. I repeat. Hold on everyone. Yes, I want you to observe the 2 groups present at the carbon in between where the oxygen is flanked, meaning we are talking about carbon number 1 and 5th. The group present at carbon number 1 and 5th are OH and CH2S. Since both are represented above the plane in the Haworth projection, that will be an indication that it is the beta anomer. On the other hand, when we will draw a Haworth projection of alpha anomer, you will see CH2OH from carbon number 5 and OH from carbon number 1 will be in the opposite side of plane. If CH2OH, if I am representing above the plane, the OH I am going to represent putting facing downward or below the plane. Alright, first let us understand how exactly are we going to name this. Now while naming this molecule, we write it like this. Since we know that it is beta, how do we know it is beta? Because OH at anomeric carbon and CH2 at carbon number 5 both are pointing upward on the same side of the plane. So this is beta. This is beta hyphen D hyphen plus. Now this is glucose, so this is gluco. Now because this is corresponding to the structure of pyrin, we write that word pyrin. and because it is sugar, we end the suffix OSE. So what we have basically done, between gluco and O's, what we have done is we have added term pyran. That's how we name this compound as beta D plus glucopyranose. Understand the meaning of every term that we are using here. Beta stand for it is a beta ionomer. OH and CH2H are on the same side. D stand for it is derived from the D family of a glucose. Plus stand for it is a dextrorotatory, or you can use small d as well. But to avoid the confusion of D and D, we rather use plus. And glucopyranose because it is resembling to the structure of pyran. Similar to this, suppose if you want to put the Haworth projection of alpha D glucose, how are we going to put it? Well, alpha D glucose, guys, I'll put alpha D glucose down here. Now, since you know beta, the only difference in alpha is going to be this OH will come down at carbon number 1 and H will go up. Rest everything remains same. So see how quickly we draw it. The fastest way of drawing this is make a skeletal ready. This is anomeric carbon 1, 2, 3, 4, 5 and this is 6th. Okay. By convention we are putting CH2H up only. Now listen to me carefully. That is your anomeric carbon, which is carbon number 1. This is 6 and carbon number 5. Everyone, I'm going to tell you how to write it in the fastest way, okay? Just to make it alpha. Now we want CH2H and OH on the opposite side of the plane. So OH, I'm putting it downward. Okay. Now see, when we were drawing open chain structure of glucose, we were following one order: right, right, left, right, 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 left, and right. It's just that the right which we used to say while drawing the open chain structure, that OH no more exists because the same OH is now utilized in the formation of this oxygen linkage. So at carbon number 5, when I'm saying right, right, left, right, I'm not going to put OH at carbon number 5 because that OH no more exists, right everyone? But for rest of carbon number 4, 3 and 2, right, left, right still exist. And when I say right, which means you're putting which means you're putting the group facing downward in the Haworth. So here, after 5, see for 5 I will just say right, but I'm not going to put any OH. So right, right, left and right. See what I'm doing? I'm saying right, but by default while I'm putting it downward. Right, 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 left and right. Remaining valencies will satisfy by H. Now see, this clearly indicates the CH2OH at carbon number 5 and OH at carbon number 1 are opposite. Because they're opposite, it is now alpha, but still family of D, dextrorotatory. So alpha D plus glucopyranose. So guys, that's how we draw a cyclic structure of alpha ionomer and beta ionomer. So a lot of information in the one slide itself. Guys, we studied why do we have to learn structure of cyclic structure? Because open chain structure does not respond to all the properties because it merely exists 0.02%. Rest 100% is alpha D glucose, beta D glucose. You know what is alpha and beta. You know what is hemiacetylic carbon. We also learned that it can reverse back to aldehyde. Hemiacetylic carbon called as anomeric carbon. When configuration differs at anomeric carbon, you call these two as ionomers of each other. If you take a crystalline form of the pure alpha and beta ionomer, you will find there's some specific rotation in aqueous solution. If you allow it to settle for some time, the optical rotation will gradually change and will settle at the equilibrium value. This change, the gradual change in the specific rotation, is what you call it as muta rotation. And then we learn how to draw the Haworth projection of alpha and beta ionomer. Make sure in alpha, CH2H and OH are on the same side of plane. In beta, they are on the same side of plane. In alpha, they're on the opposite side of the plane of the ring. Alright everyone, just like we did for glucose, now we'll have to learn the cyclic structure of fructose as well. Now this time I'm going to move a little faster. Okay everyone, see. So fructose, how do we get structure of fructose? CH2OH double bond O, number 3, number 4, number 5, number 6. Right, right, and left, and left. Remaining valencies we satisfy by H. So this is nothing but D-fructose. We have got D-fructose. Just like glucose, even D-fructose exists in a cyclic structure in its two forms, that is alpha and beta. So let us talk about alpha form first. To get the alpha form, what we do here, or rather what is observed in nature, this is carbon number 2, 3, 4, 5. So the lone pair of oxygen atom of OH of fifth carbon then attacks at the deficient carbon. This bond will break to make it O-, which will be then protonated, and this will undergo deprotonation. Now see, the cyclic structure formation is taking place via oxygen atom between 2 and 5. So number of carbon in the cyclic structure will be 1. Although number is 2, I'm just counting the number of carbon in the cyclic structure. 1, 2, 3, 4, 5. So we're going to get 5-membered cyclic structure. So the closed chain structure formed can be represented like this. Let's say I'm representing this as alpha. So CH2OH and H. This is carbon number 3, number 4, number 5, number 5. And this is 6th. Right, right, and left. Remaining valencies we are satisfying by H. Okay, we'll explain the structure. Let me first draw it here as well. So let's say this is CH2OH. Third, fourth, fifth, and sixth. Right, right, and left. Remaining valencies are just hydrogen atoms. Okay, everyone pay attention here. See what has happened now. Since carbonyl carbon in fructose is the second carbon atom, the lone pair of oxygen from carbon number 5 has attacked here. So carbon number 2 has now become newly formed chiral carbon. How chiral? Now this is becoming C single bond OH, one of the valency. Then C single bond CH2H, second valency. Then third is this oxygen linkage, and fourth is this entire group. So see, that is your carbon number 2, which has become newly formed chiral carbon. This is the newly formed chiral carbon. Right, everyone? This is the newly formed chiral carbon atom. So this is carbon number 2, and that is carbon number 5. Same way here. This is the newly formed chiral carbon atom number 2, and this is carbon number 5. So just like we did earlier, if you are putting CH2H to the right in this Fisher's projection, we will call it as alpha. So this will be called as alpha D fructose. But not to forget, naturally occurring fructose is levorotatory. So just like we were mentioning plus in case of glucose, we are going to put minus in case of fructose. This will be called as beta D fructose. Now, because this fructose cyclic structure is corresponding to the 5-membered ring, look, 1, 2, 3, 4, 5, or rather go this way, 1, 2, 3, 4, 5. Since it is forming a 5-membered ring, it is going to resemble to 5-membered cyclic structure. What is that 5-membered cyclic structure? Just like we had a pyran here, this time 5-membered cyclic structure, which we have got is nothing but furan. Okay, so how do we draw structure? Let me show you that. Look, I'm going to draw a 5-member cyclic structure. Okay, carbon number 2, number 3, number 4, number 5. Now, this is the newly formed newly formed chiral carbon. I'm not saying hemiacetylic. So that is number 2, number 3, number 4, number 5. Now look, let's see if I'm writing a beta form. So in the beta form, you will see CH2OH is your carbon number 1, which is put to the left, meaning it will be above the plane. So that is CH2OH. That is carbon number 1. And here at 5th carbon, we have got CH2OH, which is by convention we put it up. So see now what happened. Oxygen is flanked between carbon number 2 and 5. So we check the valency present at carbon number 2 and 5, or the group present at carbon number 2 and 5. The groups present at carbon number 2 and 5 are CH2H and CH2H. Both are pointing upward. Both are in the same side of the plane. So that's your beta anomer. So this is your beta anomer. Rest of the valencies, right, right, and left. Correct, everyone? Right meaning you have to put it downward. So while writing the structure of fructose, we were remembering like this: right, right, left. But the first right, which is at 5th carbon, has been utilized in this oxygen linkage. So we are going to say it, but we are not going to write it. So right, right, left. Remaining valency we satisfy by H. So how do we name this now? We'll name it like this: beta D. Now it is minus because I said fructose is a levorotatory sugar. So experimentally found fructose, if you make aqueous solution pass plane polarized light, it will rotate the plane of PPL to the left. Hence it is levorotatory. So beta D minus fructose. But fructose is no more resembling to pyran, resembling to furan. So we'll call it as furanose. So that's the Haworth projection of beta D fructose. Similarly, when we write down Haworth projection of alpha, the only difference, the CH2H, which is above the plane, you'll put it below the plane, pointing downward. So, to get the structure. Okay. So that's going to be carbon number 2, number 5. All right, everyone. So that's anomeric carbon. CH2H by default, we are pointing upward. Now, since it is alpha, CH2H to the right, meaning pointing downward. And here it is H. So right, right, and left. So that's how. Now you'll see at 2nd and 5th carbon, CH2OH, the group present are on the opposite side of the plane. One is at 5th, it is above the plane. At 2nd, it is below the plane. Opposite side indicates that it is alpha anomer. Hence, we will say the name of compound is alpha D minus, because levorotatory, fructose, furanose. Alright guys, I'm hoping that you guys are understanding how to draw the Haworth projection of molecule and all the details that we have learned here. So that was all about the important monosaccharide and their cyclic structure that we were supposed to study. And now it's time for us to learn the disaccharides. So guys, what we're going to learn here is some important disaccharides. Well, before you start learning the structures of disaccharide, first we have to understand its composition. The disaccharide is made up of which two monosaccharide units? And for which I'm just telling you one simple table. I want you all to first learn the table and then the rest of the thing. Well, so I want you all to remember first one as sucrose. Second, I want you to remember maltose. Next is lactose. All these examples are disaccharide. Disaccharide are those carbohydrates which upon hydrolysis produces 2 units of monosaccharide. And then you will remember cellulose. Okay. Now, how I want you to remember the table is, start like this. Alpha plus beta. For sucrose, alpha, beta. Then repeat alpha in the second one. Alpha, alpha. So both the times you repeated alpha. And then in third and fourth, repeat the next Greek letter, that is beta. So beta, beta, and again beta, beta. This is just a way to remember, okay? Everyone. I repeat. Alpha, beta, alpha, alpha, beta, 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 beta. Simple? Yes. Now, C1, C2. And for rest all, C1, C4. C1, C4. This number indicating the number of carbon atom responsible for the glycosidic linkage formation. So C1, C2, C1, C4, C1, C4. And C1, C4 again. And now you just have to know what monosaccharides consisting that particular sucrose, that particular disaccharide. Like sucrose is made up of glucose and fructose. So you'll have glucose. Of course, it is going to be in the form of glucopyranose, but I'm just writing the name because you just have to understand what sugar is that. So glucose and fructose. In its Haworth projection, of course, maltose is made up of 2 glucose, so it is homodisaccharide. So glucose and glucose. Lactose is made up of galactose and glucose. So remember, galactose you have to write first. Galactose and glucose. And then again 2 glucose. Cellulose is again homodisaccharide of glucose only. So you might be wondering what's the difference in maltose and cellulose. Well, observe carefully. For maltose and cellulose, C1, C1, glucose, glucose, C4, C4, glucose, glucose is same. But maltose is made up of alpha ionomer of glucose. Cellulose is made up of beta ionomer of glucose. So guys, how do we remember the table? Simply. Alpha, beta, repeat alpha, 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 then all beta. Beta, 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 beta. Alpha, beta, alpha, alpha, beta, 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 beta. Okay. Then only first we'll have C1, C2. Rest all are C1, C4, C1, C4, C1, C4. And then just know the monosaccharide. Glucose, fructose for sucrose. Then glucose, glucose, galactose, glucose, and glucose, glucose. It's just a matter of couple of minutes. If you spend 2 minutes on this writing, you will be able to remember. But guys, now imagine if you remember this sequence very well. But what if you forget this sequence? That will bring you in trouble, right? So you need to know this sequence as well. Then only this everything will fit well. So remember, the first one is sucrose. Second is maltose. Third is lactose. Fourth is cellulose. So I remember this as small c. Ignore L, small c. Just a word to remember, SMLC. Sucrose, maltose, lactose and cellulose. Okay. So this is the table ready for us. Now we know very well that particular disaccharide contain which 2 monosaccharide in which anomeric form, alpha or beta. And this, other than knowing that, we also know that these 2 monosaccharides are connected to each other through the OH group from which particular carbon. What exactly is this trying to tell is, let me just give you one example. Look, everyone, we know sucrose is made up of glucose and fructose. We know that glucose and fructose both are polyhydroxy compounds. So I'm highlighting one of the H. Similarly, even fructose is a polyhydroxy compound. We just now saw the structure. Now, although we know that these 2 are polyhydroxy compound and these 2 are connected to each other in a sucrose. How are they connected? They are connected by elimination of water, let's say if I do elimination of water from here, you will see glucose is connected to fructose via this ether type of linkage. This ether type of linkage is what we call it as glycosidic linkage. So okay, we know it is a glycosidic linkage which is going to hold these two monosaccharides together. But how do we know that? This glycosidic linkage is obtained by condensation between which two OHs group? So that information is being given here. Glucose OH present at C1. So this OH is from C1 of glucose and this OH is C2 from fructose. That's what this C1 C2 talks about. So now we know it's for sure. I'll draw Haworth projection of a glucose. Which glucose? Alpha glucose. And I'll condense OH from the C1 with the beta form of fructose through its OH from the C2, and I'm going to get the glycosidic linkage. So guys, let us see how exactly we draw the structure of disaccharides. So we're going to learn the structures of disaccharides. So we have got sucrose. Just now we said sucrose is a heterodisaccharide of alpha glucose and beta fructose. So first we'll have to get the alpha glucose ready. So how do we get alpha glucose? In the fastest way, if you have to get it, you can do it this way. Okay. C1 and C2. Okay, everyone here. One, 2, 3, 4, 5 and 6. Alright, now they're talking about alpha. When they talk about alpha D glucose, which means OH and CH2H has to be on the opposite side. So OH I'm putting downward, right? Because they're talking about alpha D plus glucopyranose. Which is going to get condensed with. So C1 of this will condense with C2 of beta D minus fructofuranose. Okay. So yes, alpha meaning CH2H and OH on the opposite side, and then this is carbon number 5. So right, we just say right in case of fifth, we don't put it, right? Because that OH is used here. So right, left and right. Remaining valencies are H's. So I want you guys to highlight that carbon atom which is going to undergo condensation. So it is going to be C1 of alpha D glucopyranose, which will be condensed with C2 of beta D fructofuranose. C2 of beta D fructofuranose. Well, fructofuranose, since it is fructo, OH and CH2H. So that is carbon number 2. This is carbon number 6. So see, in case of beta, CH2OH at 5th and CH2OH at 2nd, since they're talking about beta form. Alright, so in beta, this 2 has to be on the same side. Alright guys, hold on. This 2 has to be on the same side. OH and CH2OH. Okay, everyone here. So since we are talking about beta form, the OH at 2nd carbon and CH2OH at 6th carbon, they are on the same side. Guys, just hold on. Alpha And H. Okay, we are doing some mistake here. Hold on, everyone. So this has to be H. This has to be H. Just 2 moment, everyone. Beta D fructose. Okay, we made a mistake here itself. Guys, we made a mistake here. At carbon number 2, this was C single bond OH. So this was OH. This was also single bond OH. Little correction here. So at carbon number 2, this is OH. Okay, this is OH. See? This is C single bond OH. So here as well, C single bond OH. Okay. Now guys, little correction here. Now we talk about beta ionomer. It is CH2OH and OH should be on the same side. Guys, we are making small correction here. So we have OH pointing upward and CH2OH pointing downward. So guys, CH2OH at 5th carbon and OH at the 2nd carbon should be on the same side of the plane. That makes it beta. And in case of alpha, CH2H and OH should be on the opposite side. So it should be like this. CH2OH and OH. Yes, now it is perfect. So CH2OH and OH are on the opposite side. All right. So now while drawing the structure here, since we are talking about alpha D glucopyranose, so alpha meaning CH2H and OH are on the opposite side, and beta meaning CH2H and OH are on the same side. Yes. And remaining right, right, and left. Okay, everyone, I'm hoping that you guys got the miscommunication that was there in the previous ones. Okay, now see, we have got carbon number 1 and carbon number 2 from where we have to form a glycosidic linkage. So that is carbon number 2. Carbon 1 and carbon number 2. So when you form a glycosidic linkage, it has to be between OH of C1 of glucopyranose and OH of C2 of beta D fructofuranose. So OH from C1, OH from C2 has to be condensed. So if you condense this two, remove water from here. If you remove water from here, see this oxygen will be directly connected to this carbon number 2. So I'm directly writing it now. Okay, this glycosidic linkage is what we call it as C1, C2, glycosidic linkage. All right, everyone. So that's how you get the structure of sucrose. Now, you know the fact that we have got sucrose, which is basically a heterodisaccharide of glucopyranose and fructofuranose. So when you carry out hydrolysis, sucrose upon hydrolysis is going to give you again alpha D glucopyranose and beta D fructofuranose. Please understand, you're going to get alpha D glucopyranose, alpha D plus glucopyranose and beta D minus fructofuranose, which means one of the compound is going to be dextrorotatory, other is going to be levorotatory. So what happens to this is the new concept that we have to learn, which is called as inversion of sugar. Now what does that mean is, let's say we have got C12, H22, O11, that is sucrose. If you carry out hydrolysis of this sucrose, of course in an acidic condition, upon hydrolysis this produces C6, H12, O6, which is nothing but D-glucose, and C6H12 O6, which is D-fructose. But everyone, like I mentioned, glucose is dextrorotatory, fructose is levorotatory. So if you find out the optical rotation of sucrose, you will find the optical rotation of sucrose is found to be plus 66.5 degree. So the starting compound sucrose shows optical rotation which is dextrorotatory. Upon hydrolysis, the mixture that you are getting has D-glucose and D-fructose, but glucose being dextrorotatory, if you find out its optical rotation, you will find the optical rotation here is plus 52.7 degree, whereas the fructose which is obtained found to be showing its optical rotation of minus 92.4 degree. What does this indicate? The aqueous solution of starting compound sucrose is definitely dextrorotatory. Upon hydrolysis, the mixture which we are getting has one compound which has dextrorotation of plus 52.7 degree and another compound which is in equimolar quantity of that of glucose, because both are present in equal proportion. Sucrose is made up of one molecule of alpha D-glucopyranose and one molecule of beta D-fructofuranose. So amount is equimolar. But one of it has an optical rotation of plus 52.7, which is dextrorotatory. Other has optical rotation of minus 92.4, meaning levorotatory. So the overall mixture's optical rotation, you will see the levorotatory optical rotation is more than that of the dextrorotatory, which means the overall optical rotation of a mixture is going to be levorotatory, because levorotation is dominant over dextro. So if you see the overall change, the starting compound dextrorotatory, upon hydrolysis gives you mixture which is overall levorotatory. Such a change in the optical rotation as a result of process of hydrolysis is known as inversion, because there is a change in the optical rotation from plus to minus. So we call it as inversion of sucrose, which is also known as sugar, table sugar or cane sugar. So conversion of dextrorotatory solution of sucrose into levorotatory mixture of glucose and fructose is known as inversion of a sugar, and this mixture is known as invert sugar. So the mixture will be referred as invert sugar. Alright everyone, this is what you call it as inversion. Now let's learn the second disaccharide that we have to learn, which is maltose. Well, while learning the maltose, we'll first note down what maltose is made up of. Maltose is made up of alpha glucopyranose. So alpha connected through C1, glucopyranose plus C1 C4, so C4 alpha, again glucopyranose. All right, so here C1 of alpha glucopyranose and C4 of alpha glucopyranose. Well, so let's say this is CH2OH, carbon number 6, carbon number 5. Since we are talking about alpha, alpha meaning CH2OH from carbon number 5 and OH from carbon number 1 has to be on the opposite side of the plane. So OH I'm putting downward. This is H, rest what? Right, right, left and right. Correct? The moment I'm saying right, meaning the features right indicates in the Havod it has to be put downward, and the left in the features should point upward. So that's what I'm making sure. Right, 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 left, right. But for fifth, we never represent, so remaining valencies are just hydrogen. So see how quickly we got the structure of alpha glucopyranose. Now we have got again alpha glucopyranose, same structure, right? Two, 3, 4, 5 and 6. So that is 6, this is fifth. Again, this is alpha, meaning CH2OH, and OH should be on the opposite side. Right, right, left and right. Remaining valencies just H's. Well guys, now find out where do we want glycosidic linkage. The information says glycosidic linkage is between C1 and C4 of the two monosaccharides. So C1 is here and C4, 1, 2, 3, 4, C4 is here. So I have to condense OH from C1 and C4. So if you condense, you're going to remove water like this, meaning C1 will be connected to oxygen and to C4. So C1, C4 will be connected through this oxygen linkage. So just to make it look better, I'm writing it in a proper way. So let's say if you put it this way. Yes. So you see this is nothing but maltose, and this linkage will be now referred as C1, C4 glycosidic linkage. Okay everyone, C1, C4 glycosidic linkage. So we studied maltose. Next is lactose. Let's try to put an information for lactose. Guys, what was lactose all about? Lactose was alpha beta alpha alpha beta beta, correct? So C1 beta galactopyranose. Galactopyranose, which is going to condense with C4OH of again beta, but of glucopyranose. Guys, individually we never practice writing structure of galactose as such, right? But we know one very important information, that glucose and galactose are C4 epimers. Do we know that? So please have a note of that. Note. Glucose. Okay, D-glucose rather. D-glucose and D-galactose are what? Are C4 epimers. Okay, which means now in order to get the structure of galactose, what I'll do, I'll first get the structure of glucose, and I will only change the configuration of OH at C4 carbon. That is going to give me galactose, right? So everyone, I want to get galactose. One, 2, 3, 4, 5 and 6. Since it is beta, OH and CH2 should be on the same side. So I'm putting OH on the same side. Is it right? C1 and C4 beta. Okay, yes, CH2H and OH on the same side. Now that's your carbon number 5. Now see, in case of glucose, we say right, right, left, right. Right, right, left, right. But at the fifth carbon, in case of glucose, if OH is to the right, in galactose it should be above the plane. Why? Because glucose and galactose both are what? They are C4 epimers. So in case of glucose, if I'm going to put OH to the right at carbon number 4, I must put it left, meaning above the plane. So that is right, left, left, right. That is galactose. Okay, that's your carbon number 1. Now this is going to go under condensation with the beta form of glucopyranose. Beta form of glucopyranose. Okay. One, 2, 3, 4, 5 and 6. Carbon number 6, carbon number 5. Again, beta meaning OH and CH2H on the same side. That's your H. Now since it is glucose, right, right, left and right. Remaining valencies are just H's. Okay. Now see, when you're doing condensation, you have to identify that OH from C1 of galactopyranose are going to condense with OH from C4, which is this. So this 2OH has to be condensed, right? One is above the plane, other is below the plane. So simply we can put it this way. If you remove water from here, ideally OH and H will be removed like that. So C4 connected to O and then to carbon number 1. Let's put it in a proper way. Okay. So that is called as C1C4 glycosidic linkage. C1C4 glycosidic linkage. Alright everyone, so that was all about lactose. So we studied sucrose, small c, sucrose, maltose, lactose. Cellobios we are not doing it right now because later when we'll talk about polysaccharide, we have to learn cellulose. So cellulose is basically a polysaccharide which is an extension of cellobios itself. So anyways, we are going to use it there. So far we studied what? Guys, we studied why cyclic structure of glucose and fructose has to be studied based on the reactivity or the limitation in the reactivity of open chain structure of glucose. In the process, we learn how to write Haworth projection. We learn how alpha and beta ionomer exists, what is anomeric carbon, what is called as mutarotation. Then we learn some important disaccharide. We studied a simple table to remember the composition of those disaccharides, out of which so far we have studied drawing structure of 3 important disaccharides, that is sucrose, maltose and lactose. Cellobios, of course, we are going to see when we'll study cellulose, because soon after this what we are going to learn is some important polysaccharides. Well guys, I want you guys to go through this quickly. I'll just drink some water. I want you all to go through this quickly, everyone. Okay, everyone. So the first one we're going to learn is starch. Okay, guys. So the first important polysaccharide that we have to learn is the starch. We have seen how starch was useful for us to prepare glucose industrially. So starch basically consists of two important parts of it. That is what you call it as amylose and amylopectin. It is basically the main storage of polysaccharide in the plants, and like I said, it contains two important parts, amylose and amylopectin. Amylose is the one which constitute just barely 15 to 20% of the entire starch, and it is a water soluble starch, you can say. So amylose is water soluble component which constitutes just 15 to 20% of a starch. Remember this important information, that it is water soluble. Chemically, amylose is a long unbranched chain of 200 to 1000 units of alpha D plus glucose units held by C1C4 glycosidic linkage. Well, this is the important information that is telling us how to get the structure of starch. Guys, if you read it carefully, you will realize that this information is telling us exactly what we have learned in maltose. Try to recall what was maltose. Maltose was C1C4 alpha alpha glucose glucose. So C1C4 alpha alpha glucose and glucose. Meaning what? It just that in maltose we had 2 units of glucopyranose, of alpha glucopyranose, connected to each other via C1C4. Here there are going to be 200 to 1000 units. Meaning whatever you wrote in disaccharide, imagine if you extend that chain, a linear chain, and make it around 200 to 1000 units, that is going to give you what? Amylose. And then what comes is amylopectin. Amylopectin is water insoluble. Remember, this is water insoluble, and this is the one which constitute the maximum part, that is 80 to 85% of starch. Now, just the way we remembered the linear polymer of amylose, which is basically extension of maltose. Imagine if you have got two such linear chain. Now from the first linear chain, if you condense OH from the sixth carbon of the chain which is above with OH from the first, so if you see here, it is a branch chain. This was a linear chain. This is the branch chain polymer of alpha D glucose unit, in which the chain is formed by C1C4 glycosidic linkage, meaning exactly like this, C1C4. Now, whereas branching occurs by C1 and C6 of the glycosidic linkage, meaning whatever chain you have got, let's say if you have got amylose at the top, and if we condense OH from the first carbon of amylose with the sixth carbon of of the second chain, you're going to get a branches between them. Of course, I'll explain when we'll draw the structure. As of now, first we'll try to understand how to get the structure of amylose. Simply, the way we draw structure for maltose, in case of maltose we had 2 units, we'll take many units now. That is the only difference it is going to be. So let us draw that first. So how do we used to get maltose, everyone? Maltose was C1, C4, alpha alpha, glucopyranose and glucopyranose. So let's say we have C1, C4, C2, C3, C4, C5, C6. Right, left and right. Since it is alpha, CH2H and OH should be pointing downward. Right? This is one of the glucopyranose. Highlight C1 and C4. C1, C4. This is 1 unit. Second unit. Sixth carbon. Fifth carbon. First carbon. Again alpha meaning CH2H and OH pointing downward. First, second, third, fourth, fifth. Right, right, left and right. Remaining valencies with H's. And again, just mention the number. This is C1, this is C4. And since it is polysaccharide, we cannot stop just at 2. There has to be more. So let me draw one more at least. One, two, three, 4, 5. That is carbon number 5. Since it is alpha, CH2H and OH in the opposite side of the plane. And now, right, right, left and right. Remaining valencies we satisfy by H as usual. Again, we'll highlight that this is C1 and C4. Now see, what we have mentioned in amylose is that we have got alpha D plus glucose units held by C1 C4 glycosidic linkage. So we have to condense OH from C1 and C4. So every adjacent, like here, if you remove water like this, H2O, so this O will be connected to C4. So just the way we have been doing earlier. So everywhere I'm just keeping that arrangement ready. Again C1 and C4. Here as well C1 and C4. So see, C1 connected to C4 via glycosidic linkage. Even this C4 will be connected to C1 of some other carbon. So this is going to be, this line indicates a polymeric chain will continue. C1, C4, C1, C4, and this is going to be a polymeric chain which will continue. So guys, what is this? This is nothing but amylose. This is nothing but amylose. Now understand, amylose is a linear polymer chain where there is not going to be branching anywhere. But now when we talk about amylopectin, so amylopectin meaning this is one of the linear polymeric chain. Likewise, we will have one more linear polymeric chain down here. One more linear polymeric chain down here. But C1OH of first chain will condense with C6OH of the chain which is below that. So just to represent amylopectin. Now this is amylose. I'm making the same change in amylose itself to get the amylopectin. So see what change I'm going to do here now. Firstly, I'm keeping this OH ready for us. So let's say this is CH2OH. And now OH, CH2. One, two, 3, 4, 5. Further chain, O, further chain. Since it is alpha, right? So that has to be H. Carbon number 5. Right, right, left, and right. Rest of the valency, I'm just putting H's. Okay, now guys understand. This is carbon number 6th. So this was amylose, linear polymeric chain, let's say. And this is the terminal of that linear polymeric chain. There is likewise one more amylose, let's assume like that. One more linear polymeric chain of amylose like that. I have shown continuation. I'm not drawing every time the structure of monosaccharide. Now what we are saying, amylopectin, read the information. Amylopectin is formed by the glycosidic linkage between C1-C6 glycosidic linkage, which is showing a branching, which means now there will be a branched form here between C1 of the first polymeric chain or linear polymeric chain and with OH of C6 of another polymeric chain. So if you remove water from here, what will happen? C1O, C6 will be connected to each other. How do we show that? Like this. C1, C6 connected via glycosidic linkage. So this is the branching taking place between C1 and C6. So amylose was just a linear polymeric chain between C1 and C4 of alpha D plus glucopyranose, and amylopectin is the one which is having branching between polymeric chains from C1 and C6. So giving you C1, C6 glycosidic linkage. So what you see right now on your board is just amylopectin. If you remove this and keep only linear one, it is going to be what? Amylose. So that was about starch. The second important polysaccharide that we learn is cellulose. We must know the fact that cellulose is the most abundant polysaccharide. So if you read the information here, cellulose occurs exclusively in plants and it is the most abundant. This could be one of the informative questions that might come in the exam. The most abundant organic substance in the plant kingdom. It is the predominant constituents of cell wall. Yes, this is the one which is the important composition of a cell wall. Cellulose is a straight chain polysaccharide composed of only beta D-glucose. Well guys, now try to recall what you studied in cellobios. What we studied in cellobios, the fourth one, in small c. So we had what? We had alpha beta, beta beta and beta beta. So this was beta and beta. C1, C4, glucose and glucose. Correct? It's just that in cellobios we were having only 2 units, and now it's a polysaccharide. See, in polysaccharide, cellulose is a straight chain polysaccharide composed of only beta D glucose, which are joined together by glycosidic linkage between C1 of one glucose and C4 of next glucose, C1 and C4 of next glucose. So basically whatever we were doing for cellobios, if we extend the units, instead of keeping just 2, if we take many, then the same cellobios will be called as cellulose. So whatever we were doing for cellulose, cellobios, we are going to do for the cellulose as well. So just that instead of 2, we'll be taking many. So how do we get the structure? To get the structure of cellulose, again we need to first write down the simple information. Cellulose was beta D glucopyranose plus beta D glucopyranose through C1 and C4. Through C1 and C4. So look here. Okay. CH2OH and OH at carbon number 1, both on the same side, indicate that it is what ionomer? Beta ionomer. So 1, 2, 3, 4, 5 and 6. So right, left, right. Remaining valence is H's. So this is beta D glucopyranose. Fifth, sixth, fifth, fourth, third, second and first, because it is beta, OH and CH2H both on the same side. Again, right, Right. For the fifth, we say right, but we don't put OH because that OH is already used in this linkage of oxygen. So right, right, left, right. Remaining valences with H's. All right, everyone. And of course, since we'll have many, so we need to write one more. So I'm putting one more down here. One, two, 3, 4, 5, and 6. 6, 5. So this is beta, meaning OH pointing upward. So right, right, left, and right. Remaining valence is H's. Okay, guys, now let's try to figure out the number of carbon atom from where we are going to carry out condensation. So it's a C1 of 1 unit and C4 of adjacent. So this is C4, C1, 1, 2, 3, 4. Just like this is C4 and this is C1. So from the adjacent unit you will condense OHs. So basically this OH will be condensed with H. So if you remove H2O, so this C1O C4 will be connected. So now just to make it simpler and to make it look better, we'll make arrangement everywhere. Okay, so now we have got linkages formed here. O connected further, O connected further, O connected further. This O will be connected further, and you will get the polymeric chain. So guys, this is how the structure of cellulose will exist. Basically, you will see we have got units of beta D glucopyranose, and those are connected to each other via C1 C4 glycosidic linkage to give you a linear polymeric chain like that. So what we did in case of cellobios, we just extended that by taking many units. We got cellulose straight away. So those were some important polysaccharides. Now one more important polysaccharide left, whose structure found to be similar to that of amylopectin, just that it is more complex, and that is nothing but glycogen. So guys, glycogen is nothing but when carbohydrates are stored in animal body, they are always stored in the form of glycogen. The carbohydrates are stored in animal body in the form of glycogen. This glycogen sometimes is also referred as animal starch. Why? Starch in general we talk in terms of plants, right? Having two important parts of its amylose and amylopectin. Amylopectin is branch one. So when you talk about glycogen, the structure of glycogen is similar to that of amylopectin. But amylopectin refers to plant and glycogen refers to animal body. So you call it as animal starch. It's just that the structure of glycogen is going to be more complex than that of amylopectin. So you can see it is also known as animal starch because its structure is similar to amylopectin and it is rather more highly branched. It is found in liver, muscle and brain. When the body needs glucose, what enzyme does? Enzyme break this glycogen down to glucose. So when we need a source of energy, then this glycogen is broken down by the enzyme catalyzed reaction and it provides the glucose molecule. And then this glycogen is also found in yeast and fungi. So it is just an informative reaction. I want you guys to read it and try to remember. You may have some informative question from this part as well. So dear student, as far as cyclic structures are concerned, today we discuss cyclic structure of glucose. We studied the cyclic structure of fructose, and in between while learning lactose, we also studied the cyclic structure of galactose as well. So we studied Haworth projection, all of this. In the same process, we also learned the concept of what are called anomers, alpha and beta anomers. We studied something called as mutarotation. And as long as hydrolysis of starch, sucrose is concerned, we also learn inversion process. Other than this, For disaccharide, we studied 4 important disaccharides: sucrose, maltose, lactose, cellulose, small c, SMLC. We saw how to remember their individual monosaccharide, which together consist those important disaccharide, and how to remember their structures. And we also learned some important polysaccharide, which includes starch. Further, we studied amylose and amylopectin, 2 parts of starch. We studied cellulose, and we studied also the glycogen. So 3 important polysaccharide we studied. And now the last part of carbohydrate that we have to learn is about reducing and non-reducing sugars. Well, just to give you reference from the carbonyl compounds, guys, we studied oxidation of aldehydes. Oxidation of aldehydes, not ketone. So aldehydes can be oxidized to carboxylic acid using a moderate oxidizing agent such as Tollens reagent, Fehling solution, Benedict solution, and Schiff's reagent. And all these reagents were basically alkaline reagent, which used to convert aldehydes into carboxylate ion, and this reagent themselves used to get reduced. So who used to carry out reduction? Of course, those aldehyde. So we used to say aldehyde reduces Tollens reagent into silver precipitate via silver mirror test. We used to say aldehyde reduces Fehling solution and Benedict solution into red color cuprous oxide precipitate. Right, everyone? Now imagine if the same aldehyde is present in the carbohydrates. So those carbohydrate which will reduce Tollens reagent, Fehling solution and Benedict solution will be considered as a reducing carbohydrates. Because carbohydrates are commonly termed as sugar, such sugars which reduces Tollens, Fehling and Benedict solution will be referred as reducing sugar. Hence, in simple word, what are reducing sugars? Sugar that gives positive test, or the one which reduces Tollens, Benedict as well as Fehling solutions, are known as reducing sugar. Right, everyone? Now see, for those sugar which are not capable of reducing these reagents, now I'll call them as non-reducing sugars. So that's how we are simply classifying reducing sugars and non-reducing sugars. Now question arises, for them to be able to reduce, they need to have that aldehyde group. Because reducing Tollens, Fehling and Benedict solution are the characteristics reaction of aldehyde. So from which probably this takes us to a conclusion that only those sugars having aldehyde, that too free aldehyde, should be able to reduce the sugar. So let's clear this confusion first. First of all, we'll talk about aldehydes only. If your compound contains free aldehyde, absolutely there is no problem. It will act like a reducing sugar. Meaning if open chain glucose is given or open chain galactose is given, it is going to reduce the Tollens, Fehling and Benedict solution. But what if compound does not have a free aldehyde? What if aldehyde is present in the form of hemiacetylic part or hemiacetylic structure? So let me remind you something that we studied. Okay, guys, I'll rather put it here only. Look. This is what we call it as hemiacetylic. Correct? Now, if these hemiacetyls are brought in contact with Tollens reagent or Fehling solution or Benedict solution. Not to forget, Tollens reagent is ammoniacal silver nitrate. Ammoniacal meaning in presence of ammonium hydroxide, which is alkaline. Fehling solution is alkaline copper sulfate in presence of course, we studied that the only difference in Fehling's and Benedict is about the salt, right? We have got Rochelle salt in case of Fehling and citrate salt in case of Benedict solution. But again, both of them are alkaline. Eventually, all these reagents are alkaline. So suppose even if your sugar does not contain free aldehyde group, but contain hemiacetylic carbon, then like I said earlier as a reference, those alkaline conditions can accept H of the hemiacetylic carbon so that the sigma bond will shift and that will push away the leaving group, alkoxy group. So upon loss of this alkoxy, see what are we getting? R, C, H and double bond O. What is it? This is the free aldehyde. So imagine if carbohydrate or a sugar containing hemiacetylic group is allowed to react with the Fehling-Tollens or Benedict reagent, that alkaline reagent will convert that hemiacetylic sugar into aldehyde, and once you get free aldehyde, now this can reduce. This can reduce. What all? It can reduce Tollens reagent, it can reduce Fehling solution, it can reduce Benedict solution. Okay, but imagine instead of this, if we have a sugar which contain acetylic carbon. What is acetylic carbon? Instead of OH, both will be alkoxy group. This is acetyl. Now, even if you use Tollens reagent, Fehling solution or Benedict solution, do we see any protic H? Protic H is the H which is connected to more electronegative atom like this. Do we have any protic H? We don't have any protic H, meaning a carbohydrate or a sugar containing acetylic carbon cannot reduce. So this can't reduce. Tollens reagent, Fehling solution or Benedict solution, right? So one thing is clear, if your sugar contain open aldehyde group or a free aldehyde group, it will certainly reduce. If your sugar contain a cyclic structure where we have got hemiacetylic carbon, such sugar can also reduce Fehling, Tollens and Benedict, because they can regenerate their free aldehyde and carry out further reduction reaction. Now question arises, what if we have got sugar such as fructose, which does not contain aldehyde, it contains ketone as a group. So can fructose reduce sugar? Yes. So remember, all monosaccharide reduces Fehling, Tollens and Benedict's reagent. Why? Suppose if I talk about fructose. Fructose we draw structurally like this. And then further whatever chain it is, that chain is not important to us. But first carbon is primary alcohol, second is ketone. Now suppose if we allow this to react with Tollens, Fehling and Benedict solution, which is alkaline in nature. So this OH minus I'm showing from here, being base, will attack at H plus. Right everyone? Now after loss of this H plus ions, hold on everyone, this sigma bond will delocalize back here. This bond will go back on O to make it O minus. So see what are we getting? H, C, single bond, OH. Why was this H abstracted? Because this was acidic H, because after loss of H plus, the anion form here is in conjugation with this pi bond. So when the conjugate base is stable, corresponding compound is called as acidic. So this H was acidic because it is adjacent to the carbon, which is carbonyl carbon. So we got double bond here. Single bond CO minus, which will now accept H plus from a solvent. Let's say this O minus accepted H plus from here. Now see, as soon as H plus is accepted from a solvent, we have got C double bond C, single bond OH. What is this? This compound is called as indiol. This function of alkene with two OH. So you call it as indiol. This indiol then immediately tautomerizes And upon tautomerization, see now the tautomerization can be shown with this ene and OH, or this ene with this OH. So if I represent tautomerization from this one, so sigma bond will shift here, H will be lost as H plus, we'll get double bond here, C single bond C. Now this anion will accept H plus either which is lost or from the solvent. So what will we be getting? H, C, this became double bond O, HC double bond O, this will become single bond C, carrying H either from the H which is lost or from the solvent, and OH, and the further chain. Guys, what has happened? The ketonic group of fructose have been now converted to an aldehyde group which is in equilibrium via indiol. So the fructose which we had, although fructose contains the ketonic group, still it is capable of reducing Tollens, Fellings and Benedict solution, because in an equilibrium in an alkaline condition it gets converted to aldehydic, which is through the indiol formation. Hence we say all monosaccharide, whether it is glucose containing aldehyde or fructose containing ketonic, will certainly reduce Felling, Tollens and Benedict solution. So some important points we are writing down over here, everyone. All monosaccharide, you can simply remember these conclusions. This will help you to solve the questions. All monosaccharides are reducing sugar. Right? Second, except sucrose, all other disaccharides are also reducing sugar. All other disaccharides are reducing sugar. Okay, and polysaccharides are non-reducing. Because there is neither free aldehydic nor hemiacetylic group present, polysaccharides are non-reducing sugar. So everyone, this conclusion you can remember, all monosaccharides are reducing sugar, except sucrose, all other disaccharides are reducing sugars, and polysaccharides are non-reducing. Now see, when you talk about disaccharide, why sucrose is not reducing is, let me just show you structure to explain that again. When you talk about sucrose, where is sucrose? Here is the sucrose. Now see, for a sugar to be reducing, at least in any one of the monosaccharide part, there has to be hemiacetylic carbon, because hemiacetylic carbon is capable of regenerating aldehyde that can reduce the Tollens Felling solution. So if you talk about sucrose, what are the hemiacetylic carbon? In the glucose part, carbon number 1 is hemiacetyl. Carbon number 1 is the one which is anomeric carbon. But see whether it is hemiacetylic anymore. Hemiacetylic meaning there has to be OR and OH. Now see, at this carbon it is OC meaning OR, and this is again OC meaning again this is OR. So this carbon is acetylic in the combined form. So this part of sucrose cannot reduce. Also this part. Now since this is fructose, this is the anomeric carbon. Look at the anomeric carbon. For this carbon to be reducing, it should be hemiacetylic. but even this is acetalic. How? OC meaning OR, and again OC meaning OR. This OH is not directly connected to carbon 2. There is carbon 1 here. So even this anomeric carbon is in acetalic form. Because both the part of sucrose are acetalic, they are non-reducing. But otherwise, if you check any other disaccharide, let's talk about maltose. This is going to be reducing. Why? Okay. In the first part of molecule, there is no hemiacetalic carbon. Look at this anomeric carbon. OC and OC. Fine. So this part cannot be reducing. But look at this. Look at this anomeric carbon. OC meaning OR, and this is OH. OH meaning indicating that this is hemiacetalic carbon. Imagine if you use Tollens reaction. So base will accept H plus. This sigma bond will shift here. This will go back. So you're going to get C double bond O and this H. So aldehyde will be generated back. So yes, that's why maltose is going to be reducing. You can check other also. Let's talk about lactose. In the left hand side part, we have got OC and OC. So this is the non-reducing part. But this part is reducing. Look at this anomeric carbon. OC and OH. So imagine if base takes up this H, sigma bond will shift here, this bond will break. So you're going to get O double bond C, single bond H. We will get aldehyde again. So in case of disaccharide, if any one of the part is having hemiacetalic carbon, it is going to be a reducing sugar. And that's why maltose, lactose and cellobiose are reducing sugar. So guys, that's why we have mentioned that over here, that except sucrose, all other disaccharides are reducing. All monosaccharides are reducing sugar, and polysaccharides are always non-reducing sugars. So guys, that was all about our important part of carbohydrates. We have covered all the important details of carbohydrate. Do remember that small correction we made while writing the anomeric form of fructose. We just missed out on OH. We were just writing H, but make sure that you don't do that kind of mistakes. Guys, that is it from our lecture number 2 of biomolecule, where we have finished carbohydrates completely. In the next class when we meet, that is the last lecture of biomolecule, we will be covering alpha amino acids, proteins and nucleic acid. I'll see you there. Do revise what we have learned here and solve more and more questions on this, guys. I'll see you soon. Thank you, everyone.